Okay. So in a distributed environment, we have seen the consensus which is required in a distributed blockchain system or in Bitcoin. So the consensus which is proposed is your Paxos is one. In that Paxos, it is theoretically it is discussed, but implementing Paxos is little bit difficult task, a challenging task. So what happens in Paxos in generally, there will be a proposer and there will be a set of your acceptors like acceptor 1, acceptor 2, acceptor 3. Then from when this proposer proposes a particular value, all these acceptors will receive that value, and then the majority of the acceptors vote will select the value whether go with this proposer or not. If majority, then they become your learners. If majority of your acceptors are not accepting, suppose the value which is proposed by this proposer 1, then at a random period of time, all the nodes they become, they wait to collect any new proposals. And if that new proposer, again, that will be broadcasted among all the acceptors. If they accept, then majority of the acceptance, then they will go with any one value. So then there is a possibility of, we have seen that if there are multiple proposers, then from these multiple proposers, the majority of acceptor, based on majority of acceptor, whether they will go with the value proposed by proposer 1 or proposed by your proposer 2. So then once everyone learns that, okay, proposer 1's value is accepted, then proposer 1 take the responsibility to collect all the transactions from that group and build a block, and that block will be added to the blockchain. Right? That is what we have seen here. But to implement it, every time creating a block, every proposer needs to undergo with the cryptocurrency as well as your the security and privacy. So for that, they need to create a unique identification, so they follow the hash function. So again, that is the confusion task or challenging task for implementation. So then by following the basic concepts of your Paxos algorithm, the another algorithm which was derived from this Paxos is your raft algorithm. So in this raft, again, it is also a closed group, right? Closed group of the trustworthy users or servers inside the network. In that case, instead of these proposers, acceptors, and learners, in this raft algorithm, they created first every node in the network, they are followers. And then from these followers, if the concept here is, the first is every node is trustworthy first. In this case. Second one is, it is a closed group, and inside the group, every node, they first at the mode of your follower mode. Why? Because they try to listen the network, is there any leader exist in the network or not first. So every node at the initial stage, they will be the follower. If while listening the network, if the node finds that there is no leader posting any messages, in that case any one follower become the candidate for election. So in candidate, the leader, to become the leader, the candidate is requesting a vote by sending a request vote concept, and they also mention their term. What is the term? Whether in the first term or second term or third term. So we write that term as your suppose number nth term. So by receiving this request to vote with the new term, new time, then the other users in the network, they compare that request to vote term with the previously received one. If this request to vote term is, the outdated, suppose, then they ignore this request vote. If it is updated one, they will respond to this request vote as a grant, permission granted for candidate. So upon collecting the majority of the grants from the network, your candidate becomes the leader then. So in this, the first step is electing leader. Is the first step that simplifies, all the other, the drawbacks of your taxes. So once the leader is elected, then leader is all other nodes become the followers once leader is elected. So every time all the followers, they try to listen to the leader. Is there any new transactions created by the leader? So those, if any new transactions are accepted, collected by your leader, and that will be first added into your log replication first. And that log replication should be synchronized among all the servers in the network or all the nodes in the network. Once all the nodes synchronize that log replication, then your replicated state machine will be execute that smart contract. Once it is executed, that means the added transactions are committed. Then they will add it to the blockchain. Right? So that is the simple procedure difference between your Paxos and your Raft. In both the cases, this consensus algorithm, they are used for your closed trustworthy group only. That was the assumption of these two algorithms. But there are the possibility that any one node in that closed group may become the misbehavior node or malicious node. So then that kind of, in that case is how these agreement or all the nodes comes for a single agreement or the consensus. So to understand that, if any node in the network becomes the malicious node or misbehaving, then that node we called as your Byzantine node or misbehaving node. So to understand this Byzantine or misbehaving node or this particular class of problem, by considering the example of the army general's problem, from where we try to understand what kind, how the problem is stated here and addressed, and then we try to find what are the different solutions for this Byzantine general's problem. So in this Byzantine general's problem, it addressed that the army wants to attack a fort, any fort. So then they divided their army groups into separate troops. So those troops are surrounding this fort to attack. Right. So that is the Lieutenant 1 troop and Lieutenant 2 troop. And the concept here is based on this commander or generals ordering. Based on this ordering, they are going to attack this fort from different sides. So in that case, based on this commander attack, they will try to attack this fort. Is first concept. Second is, in Byzantine general problem, how it is going to be addressed, we'll see in the 3 Byzantine problem. But here let us see that commander is given an order that attack the fort now from the different side. So the Lieutenant 1 and your Lieutenant 2, they both received the same order from your general, so that order is attacked, so they start attacking on this fort from different side. So there is no problem. Or the condition here is either attack or retreat. Either attack or retreat, these are two commands will be given by the commander. So based on these Lieutenant 1 or Lieutenant 2, they try to attack on this. So here they follows the Lamport term decision that these lieutenants, they try to exchange the message which is received from the commander through the message exchange protocols by following the RPS, the remote procedure called message exchange protocol. Okay, but in that case, if they receive the same command, then they understand that commander is given attack order, so they will go and attack. But if the commander becomes fault, suppose, if the commander becomes the malicious node here, that means what? The commander is giving the different order to your different troops, suppose. Assume that commander is giving, become the fault, the commander is giving attack order to the Lieutenant 1 and the retreat to your Lieutenant 2. Then what happens here? There are two troops handled by the commander, and commander is behaving like malicious Byzantine here, giving some order to one attack and some order to the another troop. Condition is the entire fort should be attacked by or retreat by these different troops at a time, surrounded by these troops at a time, so that they can win that. But the commander becomes the malicious behavior here, and giving that one troop you go for attacking and another troop you go for retreat. What it means? The commander itself is making the troops in trouble, right? If they are separated, one team is just silent and another team is going for. So in the same way, inside the fort they may have some security. The commanders, right? They may easily attack this single commander, the lieutenant troop, and they can collapse them, right? If at a time all the lieutenants try to attack, then whoever are there inside this to protect this fort, they may not handle them, right? Because from different sides they are going to attack. So in that case, it assumes that this commander is got some money or because of some malicious activity. He himself put there, he or she himself put or herself put this group into trouble. So this problem we called as the Byzantine problem. This problem is treated as your Byzantine problem. So how to solve this then? So in Paxos and Raft's algorithm, which heavily it may be your Paxos or your Raft. So they basically they both relies on the fact that if there are faulty nodes, suppose inside the network, if there are any faulty nodes are there, the condition is faulty nodes will not select or will not give vote for either proposer or your leader election, correct? Only the active nodes or trust honest nodes will allow for the electing the leader or selecting the proposer, in that concept. But whereas in this Byzantine, such particular assumption does not hold in this case of your Byzantine, because the behavior is changed here. There in Paxos and Raft, assumption is maybe because of crash of your node or network fault. They may be out of the network or they may not respond to the messages. But whereas here the behavior is changing. So this general class of fault in distributed the network under the closed environment is called as your Byzantine generals problem or Byzantine fault tolerant system or Byzantine fault tolerant problem we call it. So how to address this? So let us consider the try to build an architecture for solving this Byzantine generals problem by treating if there are three lieutenants are there are three Byzantine general problem, and then if it gives the solution then that's fine, or else we try to find another architecture to solve this Byzantine generals problem which was proposed by the various authors that we will discuss. So as we said that if commander become fault, then we need some consensus mechanism to decide who is faulty. Is it the commander or is it the lieutenant one? Is it the lieutenant two? So to solve this, someone requires the method that they follow, the Lamb-Corto method. In that case, whatever the messages or orders received by these lieutenants, they try to exchange that message by following some message exchange protocols, and based on that they decides that lieutenant 1 exchanging the information, I got attack, and whereas the lieutenant 2 exchanging the message with the I got the retreat. Now in this case, now tell me, is this network or is this problem comes to a consensus here now? Not. Because there is no majority of acceptance here, right? So this is a problem. Because only because based on this information exchange, they will be in confusion, right? They don't know what to do now, what to do at this condition, whether they go for attacking or whether they go for the retreat, right? So to overcome from this, we must reach to the consensus, and in that consensus, suppose if there is a good commander can give this, go for attack and go for the retreat here. But in that case, if any one of your lieutenant become the faulty, suppose. So in that faulty also, solving this problem is again a difficult challenge. So consensus is not possible with one commander and two lieutenants in this Byzantine generals problem. Okay, and when one is faulty, it is difficult to decide whether to go with the attack or go with the retreat in this architecture. So if you go with the Byzantine generals problem with, there will be three lieutenants suppose and one commander is there. So as based on this, we have three commanders, or we call these lieutenants. So in this case, if the commander is suppose faulty, there are three lieutenants and asking that attack this fort from three different sides, from this side, and suppose from this side, attacking this. Okay. Then if the commander is faulty, suppose in this architecture, okay, if the commander is faulty, then commander is trying to give the order for your lieutenant 1 and lieutenant 2 as go for your attack, and for lieutenant 3, the third group is giving the order that retreat. Okay, so as the problem defines that once these orders are received from your commander by these lieutenants, they themselves try to exchange the messages, because once the commander is given order, then the commander is out of the picture. Only the receivers, they try to exchange their information which is received from the commander. Got it? So then they try to receive the commander and they exchange their information, whatever they received the order from the commander. So Lieutenant 1 exchanging that, he received attack, here see. So Lieutenant 1 exchanged this information or share this information with your Lieutenant 2 and Lieutenant 3. So that means at the Lieutenant 3, if you see the order of your the message which is received, first one is your retrieve, the retreat, and second message received from your Lieutenant 1 is the attack, and in the third step from your Lieutenant 2, your Lieutenant 3 is received the message again, attack now. So similarly, if you look at this Lieutenant 1 first received a message or the order as your attack. So then from the Lieutenant 2 again received the order as your attack. Then from Lieutenant 3 received the message as your retreat. So similarly, at your Lieutenant 2 first received this message attack from your commander, and from your Lieutenant 1 received the message attack only, and from Lieutenant 3 received the message that is a retreat. Right? So now tell me, is this Byzantine general's problem with 3 lieutenants will be solvable or not solvable? If solvable, then how? Based on this concept. Now, in this scenario, what will happen? Will they go for attacking or retreating? Yes, please.
They should attack.
They should attack, yeah.
Because we have a 2/3 majority saying attack. So once the lieutenants have talked to each other, we see the pool of attack, retreat. So everyone says, "Oh, there were 2 orders to attack. We attack."
Okay. So that's the good observation. Yeah. So everyone is having 3 different messages now. Out of 3 different messages, they are going to find which message is the majority one here. So out of these 3 messages, the majority at Lieutenant 1 is 2 attacks and 1 retreat. Similarly, at Lieutenant 2, the majority is 2 attacks and retreat is 1. Similarly, at Lieutenant 3, majority information which got, order which got is 2 for attack, this, and this one is 1 for your retreat. So then every lieutenant, they try to decide based on this majority response. Majority response is saying attack, though your faculty, the commander is faulty, they will go for attacking. So this is, also a concept of the majority selection process which we discussed during the permissionless blockchain system also. Okay. So then they will go for the solution for the attack. So majority is 2 is there, so they will go for attacking purpose. So it will solve. So what the condition requires to solve this? Yeah. So before going to discuss that, let us see instead of, suppose the commander is faulty, if any lieutenants becomes the faulty, will this problem will be solvable? Now the commander is good, okay, behaves, the gives a good command to all the lieutenants. Now these lieutenants receive this command and become the faulty, suppose. So this faulty, if you see here, he gives one information to one troop, another information is to another troop. So one is the malicious information, another one is a true information, true message. So the faulty told them, sending this true order to the lieutenant 1, and the lieutenant 3, receiving the what you call the retreat, that is the malicious order. So here the same information will be shared by your lieutenant 1 with other lieutenants. So then they finds that again there will be 3 messages in total out of 3. Assumption is, all should go for the attacking, but once they exchange their information, they reach that there will be this faulty is receiving, there will be 3 attacks, there is no retreat, but your lieutenant is receiving the 2 attacks and 1 is retreat, and lieutenant 1 they received, there will be 3, the attack information, and then assumes that there is one faulty in this. So majority is your attack 3. So here in this case the majority is attack 2. So go for the attacking. Here the majority of order is attack 3. So go for the attacking. And this side also, the lieutenant 1 troop also go for your attacking. So then they reach the consensus is reached. So in this scenario, from this, in the Byzantine general problem with 3 lieutenants and 1 general problem, it can be concluded that if we have the faulty nodes in this network, suppose in this case, then how it will be summarized? That means in general, to ensure the from this example we just observed that when all the correct lieutenants follow the majority voting principle, then although commander is a Byzantine node, then your all the lieutenants they go for they can correctly decode the message and go for attacking or go for retreating. But however, if the commander sends an attack message to more than 1 lieutenant, suppose, and then using the majority voting principle, they can analyze and decode that they are going for the attacking here. But when the commander is faulty and the system will reach a consensus with the value that the commander has proposed to the majority of the lieutenant. So in general, to ensure the correct consensus in the system, and when there is a maximum of the F faulty nodes, suppose the maximum of your F number of faulty lieutenants, and then there should be if F number of lieutenants are faulty, suppose this case, then to reach to a consensus, it requires 2F plus 1 node should be, or 2F plus 1 number of lieutenants plus 1 your communication in the system, where F is your faulty number of nodes. So to achieve this problem, the Byzantine, the general model, we assume that if there are n number of processes which are out of which at most F number of the processors can be faulty, while ensuring that the system has a total of your 2F plus 1 number of your processes, the system should be fully connected and receivers always know the identity of the sender, and the other requirements are that the system should synchronous and having a reliable communication medium. So the synchronous systems means that every process should receive all the messages within the predefined amount of time. Then only they can go for any decisions, either go for your attacking or go for your what you call the retreating purpose. So this is the Byzantine three general problem. So is there any limitations in this the solution for this three I mean three lieutenants problem? Yeah.
I just have one question, which is, we've seen faulty nodes that will send messages. Is there the possibility of having a faulty lieutenant who will act incorrectly?
Yes.
So then I think that could be an issue, because if we have the requirement of everyone being on the same level, if we have our faulty lieutenant decide to retreat, then in this case, an attack requiring 3 successes would fail because one of them decided not to.
Yeah. Yes.
Byzantine states that they will all almost follow. But if there are more than 2 states of the 14, then we will be talking of wrong consensus.
That's a good point. Yeah. In this case, in this architecture, in this three generals lieutenant architecture, if any one of these node is faulty, any one node, then it will be detectable and they go for the majority decision. But if suppose the commander as well as your lieutenant both become faulty, suppose more than one faulty node in this
Yeah.
three, one general and three lieutenant one. In that case, it is difficult to detect whether they go for attacking or go for retreating. So assume the same thing here in this. Suppose this lieutenant also becomes the faulty. Suppose then this he will send the information that faulty. So here also receiving faulty, here also receiving faulty, but from receive that what you call they become the equal here. Suppose so more than one faulty node presents if it is there in this three Byzantine problem, it will not detect. So it will limit to maximum one faulty and the f plus one non-faulty nodes. One faulty plus your non-faulty nodes plus one general, then it becomes your the 2f plus your 1. So it is simply says that there will be one what you call the general and maximum 2f nodes must be non-faulty to reach this problem. That means one general and two lieutenants should be lieutenants should be non-faulty. So this is the one of the major idea. So the main idea that is the synchronous one. In asynchronous Byzantine agreement, it requires 3f plus 1 nodes to reach the consensus in the asynchronous node. So f faulty nodes and needs the 3f plus 1 nodes to reach to the consensus. So what it means, the faulty nodes create the partition in the network. If it is a closed network, the faulty nodes creates the partition. When they creates the partition means whether to go with the majority of acting nodes or not, how they must be go for voting purpose, right? So examine here, there is a network with the 3f nodes. 3f nodes, that means there are total 12 nodes are there here. So there will be a 3F faulty. So to all these 3F faulty nodes comes to a consensus, means it requires one more additional node to get the decision or to get the majority acceptance. Suppose in this 3F network, if this nodes, this faulty number of nodes, when they are partitioning the network, then they partitioning that partition left nodes, partition the right nodes, so they all are equal in number, right? In these nodes, if you count that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Similarly, here also you'll find 1 to 12. So on both the partition, they are having the equal number of nodes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this we call network of network. If there is a, the group, three different lieutenants. In lieutenants, they are leading three different troops here. In that case, if any one group is partitioning equally on both the side, then they must comes to a conclusion that whether to go with the majority of voting or not. For that, it requires one additional, the faulty node to decide whether go with the left side decision or the right side decision. So for that, it requires to add the one more nodes because they are equally having here. So if one more, either PR or PL must break this tie, whether go with the attack or retreat. This bigger network. So in that case, to solve this problem, put one additional node to your PL or your PR. So that becomes your F plus 1 node. So if this F plus 1 node adds either L side, then they will go for your attack, or else if this is added this side plus 1, they will go for your retreat purpose. So by putting this additional one, that breaks the tie to reach the consensus, or else they have to wait for a random period of time to get the new order or new message exchange. So from this, as we said, the main idea of your Byzantine fault tolerant consensus that followed the Lamport-Shostak peace algorithm. So the main idea behind this algorithm is there is a commander and n lieutenants. There will be one commander, this, and there will be n number of the lieutenants here. Consider this. So the commander initiates the process and sends an initial message to all the lieutenants in the closed network. And later, each lieutenant forwards the value which is received from their commander to other lieutenants, except the sender. Except the sender means except your commander, right? So at the end of the rounds, all the lieutenants must have having the n minus 1 values, except the offline lieutenant. Except the offline lieutenant, those who are sending, they will receive n minus 1 messages, right? So this is one of the first algorithm for Byzantine general problem solution by following this. So that is happening in the synchronous environment or your reliable communication. So that is the base condition for your commander in this case in Byzantine fault tolerance condition is they send the, let me just write there will be a commander here, and you will find the lieutenant 1, lieutenant 2, lieutenant 3. So your commander initiates the order, right, and broadcasts that message. So in that, it called as the assumption, the condition for this commander, we call that the pulse. The pulse 1 is the initial pulse wave. The commander sends this message to all the lieutenants that broadcast the in that pulse it will broadcast that n at what time it is going to be given that timestamp. So broadcast this pulse to n means what? Broadcast this pulse to the n lieutenants. So in this case, suppose there are 3 lieutenants. So this n is equal to 3 here. At what time? Whether this order is the new one or the older one, to know that, as we use the terms in the Raft algorithm, here it used the timestamp as t is equal to 0 time or t is equal to 1 time. So it will be updated, where n is the number of processes and your t is the parameter that denotes the individual rounds here, the first round, second round, third round, and like that. So the commander decides when this pulse is sending to all them, that is, gives that retreat commander, message. It goes to every lieutenant here. They'll receive this. Okay. Then the commander decides, his own value, and in the closed possible values, just send the retreat or the attack. So in this example, n is equal to 3 has the 3 different lieutenants and trying to reach the consensus. So the base condition for this lieutenant is each lieutenant receives the message from the commander and checks whether it is a pulse 1 message or not. If it is a pulse 1 message and the sender is the commander, accept it. Otherwise, wait for a pulse 1 message. Then, suppose a pulse 1 message is received, then broadcast this message to all other the processes inside the network. So all the lieutenants broadcast their values to the other lieutenants by sending whatever the received message is there. By exchanging these messages, and then they will check it out, this pulse and their updated information. So that is the basic concept which is we just discussed in this Byzantine. So it says that it must be the Byzantine fault tolerance network, in that it must be synchronous environment, means within a given time period, all these messages should be exchanged by these lieutenants so that there will be up-to-date information to get the standard decision. And when they are trying to exchange these messages, the reliable communication channel should be there. That means there should not be any packet loss. Means it says that synchronous environment reliability is required, means what? The packet or message, when they are trying to exchange with this information, because of network fault or because of network problem, the message should not be dropped. So that is possible. That means there should be a reliable, means they may use the TCP protocol concept, 3 handshake process concept. In that, for every transmitted message, they wait for the acknowledgement. If within a time, speculated time, if unable to receive the acknowledgement for that shared message, then they must retransmit it. So by that way, the reliability will be achieved, and they must be fully connected, means every node connected to every other node. And their receives always know the identity of their sender, so who is sending, and so the receivers, they always knows whether the message sent by your L1 lieutenant or L2 lieutenant or L3 lieutenant. So that gives their identity. So this was the concept which was introduced by your Lamport, the and Leslie and the Robert Hooke in their first problem identification, that is the Byzantine general problems, which was they published in this ACM transaction in the year in 1982. So based on that, they addressed a lot of issues, and many discussions have made on this, and after that they try to find out this appropriate solution for the what you call the Byzantine uh, three generals problems, and another architecture that we are going to discuss about the Byzantine, the four general problems. Yeah.
Is the Lamport in this uh, algorithm the same Lamport as the Lamport signatures? Were they the same person?
Yeah, yeah,
Okay.
yeah. So actually, this Byzantine, problem, general problem, and their solutions are addressed by these authors. By considering that if there are any malicious nodes in that closed group also, how to find a solution. For that, they took the example of that the army generals problem, and from that problem, they designed a method that majority should be accepted. So majority should be accepted means the network should, what is the basic property of network means it must be synchronous, everyone reachable to every other one. There is no data loss or packet loss in the network, and every node knows every other nodes, and they identify those users means what? Their identity is there means who is doing the mischievous things can be identified. The extension of this is the research extension for this one is if you find that there is a faulty node or a misbehaving node, you must avoid that node from that network, ignore or remove that node from that network. So for that, what are the properties required? There is a problem that because of the behavior of that node may be because of two different reasons. One, unintentional reason. Another one is intentional reason. Unintentional reason means what? The attack message sent by one lieutenant to other, some lieutenant 1 to 2 suppose, is the right message. When trying to send that message to lieutenant 3, by that time, maybe your lieutenant become inactive or busy with some other, so that unintentionally that message may be delayed or message may be corrupted during the transmission. Okay. Intentionally means that will be. So how to decide that? We call certificate revocation. So we are not going into that. So in this case, the unrealistic assumption for this real network to solve this problem, there are many different variants of your Byzantine fault tolerant the consensus have emerged, but one of the most useful and the what you call in a solution which is solved for the asynchronous mode is your practical Byzantine fault tolerant system with PBFT. So that uses this PBFT uses the cryptographic techniques to release the unrealistic assumptions. So cryptographic techniques means again it comes to identify those the nodes in the network and remove those nodes from the network. So the real system mostly behave the asynchronously, so such as the nodes may not receive the message within a given time period or a given time duration. So according to the impossibility theorem, which we have addressed, that FLP, so it states that in a pure asynchronous environment, the system will not achieve this consensus, right? So the presence of faulty node is there. In that case, getting this realistic the network. Assuming that every node will be in the synchronous environment is difficult task. These are because some nodes processing speed may be high, some nodes processing speed may be low, or the network link which is connected to those nodes, maybe that because of the bandwidth, the package transmission may take longer time. So because of that, the message may not received, but later it received, but the receiver assumed that the message is not received, so gives the negative acknowledgement for that message. So that system cannot ensure the liveness property. So to ensure liveness, we need to relax the asynchronous conditions that we call the weak asynchronous environment. So we will see how the system achieves this consensus, or the ensures the safety property and liveness in the closed and asynchronous environment, and the liveness property in the closed and weak asynchronous moment that we'll try to discuss in the next class. So I would like to stop the session here.